This is Classtime Math and Compounds. I'm going to go over these problems very quickly. Please note that in problem 1, all I did was find the molar mass of the two compounds, and all I did was list the elements for each one, count them according to their subscript, multiply that times the molar mass found on the periodic table, resolve that math, and add the whole shebang up. Question 2 asks us to arrange the following substances in order of increasing mass percent of carbon. First thing that we needed to do was to go ahead and find the mass percent of carbon in each one. In order to do that, we had to find the molar mass of each one. And then once we found the molar mass, figure out which proportion of the whole compound was made up of only carbon. So I took the amount of carbon in this one divided by the whole times 100. So A had 49.5%, B had 42.1%, and C had 52.2%. So increasing mass, it would have gone B, A, and C. Okay. For question number 3, there are two binary compounds. Remember, binary means two elements that contain mercury and oxygen. Heating either one of them results in the decomposition of this compound with oxygen gas escaping into the atmosphere while leaving a residue of pure mercury. So they tell us they heat both of them, and the first one they tell us that they start out with 0.6498 grams, and then the residue is 0.6018. Obviously, the difference between the compound and the element reflects the amount of oxygen. So we can do a little subtraction and we figure out that's how much oxygen gas was liberated into the atmosphere. All I do for that is an empirical formula problem. I take the mass, divide it by the molar mass, and I come out with the number of moles for both elements. And then I compare the ratios, and I see the ratios are in 1 to 1. Therefore, the empirical formula of that first compound is HGO. And then in the second compound, they tell us that we start out with this much, and they tell us the oxygen residue that they found was 0.016 grams. And I did the exact same thing there, and this time I found out that the ratio between the mercury and the oxygen, where there's twice as many moles of mercury as there were of oxygen. Therefore, the empirical formula is HG2O. All right, now the question everybody has and gets confused is, why is the 16 when it says O2 there? Remember, we are using this O2 as a reminder that the oxygen came from this compound. All right, and the oxygen that we would, the molar mass of the oxygen here would be 16. Okay. Number 4, we're just finding an empirical formula and then the molecular formula. I remember anytime I'm giving a mass percent, I change that mass percent into a grams, and I've done that. And I check out the relationship, the moles to each other, and I see that nitrogen is in a 1 to 2 relationship with oxygen. There's 1 mole of nitrogen for every, and there are 2 moles of oxygen. Therefore, the empirical formula is NO2. Then they ask us for the molecular formula. In the molecular formula, they always have to tell you what the molecular mass is. Here it's 92 grams per mole. So we figure out the empirical formula's molar mass from here, and we figure out it is 46 grams. To find the molecular multiplier, I take the molecular mass, molar mass, divided by the empirical molar mass. That gives me a multiplier of 2. Therefore, I multiply each subscript from the empirical by 2 to get my molecular formula, and I have done that. I'll do 5 in a moment. It's really big. I didn't give myself enough time to do that. Okay. Number 6 says that the complete combustion of a sample of a hydrocarbon in excess oxygen produces equal molar quantities of carbon dioxide and water. Which of the following could be the molecular formula of the compound? Beware when you're not given any numbers in a problem. In this case, when they said equal molar, I was able to use any number that I wanted. I chose 3. Choose whatever you like. It is easier if you don't choose one. So I said that this complete combustion of this hydrocarbon resulted in 3 moles of CO2 and 3 moles of water. I figured out what the empirical formula would be using that, knowing that all of the carbon in the CO2 came from the hydrocarbon. So I asked myself, how much carbon was in the 3 moles of the CO2? I know that 1 mole of carbon contains 1 mole of carbon dioxide contains 1 mole of carbon. Therefore, I have 3 moles of carbon, and all of the hydrogen in water came from this hydrocarbon. I have 3 moles of water. 1 mole of water contains 2 moles of hydrogen. Therefore, I have 6 moles of hydrogen. I am going to try to get a empirical formula by dividing by the lowest. Therefore, my ratio is 1 mole of carbon for 2 moles of hydrogen. The empirical formula is CH2, and the molecular formula would be any multiple of CH2, and that is answer choice number C. Now, the mass percent of carbon in pure glucose is 40%. You can figure that out mathematically. However, a chemist analyzes an impure sample. That means that there is something in the sample other than C6H12O6. And it determines and when he does a combustion reaction, he recovers 38.2% of the entire sample is carbon. What impurity could account for this low mass percent of carbon in the sample? So what they're saying is something in there is taking away the mass percent of carbon. The carbon mass is relatively too low, which means the amount of hydrogen is relatively too high and the amount of oxygen is relatively too high. The only impure additive in any of these that would result in that low carbon, high hydrogen, high oxygen would be water, H2O. Okay. Now I'm going to go back, and for number 5, they said they gave us mass percent of NutraSweet, and they would like us to find the empirical formula and the molecular formula, and they've given us a molar mass for the molecular formula. This is a very easy but laborious empirical formula. I find the number of moles of carbon, the number of moles of hydrogen, the number of moles of nitrogen, the number of moles of oxygen. Then I divide by the smallest, which happens to be the nitrogen, so I can get a ratio that has a number 1 in it. And I come out with 7 moles of carbon, 9 of hydrogen, 1 of nitrogen, and 2.5 of oxygen. We know we cannot have a non-whole number in an empirical formula, so I multiply everything by 2, which brings me to this formula. When I find the the molar mass for that empirical formula, it's 294 grams per mole. The multiplier for the molecular formula is the molar mass of the molecular over the molar mass of the empirical. In this case, they are the same. The multiplier is 1. Therefore, the empirical and the molecular formula are the same.